Clam is the Community Land Trust Association of West Marin. Started in the late 1990s in a dialogue around a dinner table, and people just sort of dreamed of the need for this community to be inclusive and that we needed to grow an affordable housing stock for workers here in West Marin, people who work here but can't afford to live here, and people who are jumping from one place to another one year after the next and can't find any permanent place to call home. So Clam was sort of born around that spirit. Our mission is to provide stable, permanently affordable housing in an environmentally responsible way in all of the communities surrounding Tomales Bay. So that's kind of who we are, and I'm going to have my buddy Terry talk to you about how is a small little affordable housing organization like Clam deciding to get involved and invested in trying to do something that's never been done in the state of California. So Terry, how'd that happen?
I stumbled into passive buildings about 6 months only before I brought it to Clam, and when I first brought it, it seemed like there was a lot of blank looks and resistance.
A few of us came out and gave a presentation.
That's right.
Full of numbers and facts and slides, and then we walked away thinking, oh well, that was a go.
After that presentation, Clam was still actually really reticent about what Passive House was and could be. And at that point, we were looking at the Blue House, the retrofit remodel of the Blue House.
He renovated the Blue One house to almost Passive House standards, and so it became a low energy building. It was really exciting to see how he was able to do that cost effectively with just simple gestures. And then, so I thought that was really, big step for them to see it being done inexpensively, and that they could then have this opportunity.
Yeah.
So it was pretty exciting when they then said, let's do the next one as a Passive House.
Welcome to the groundbreaking ceremony on behalf of the Clam Board of Trustees. This is an exciting day for Clam. It's our first groundbreaking of our first affordable home that we are building from the ground up. This house is the first for Marin and California, the first new house built to the rigorous, super energy efficient passive house standard that you'll hear more about later. And this is the first passive house in the U.S. to serve permanently as affordable housing. Yay! This house is being built with tremendous volunteer and community involvement and will be held in trust for the community by Clam. Thank you for coming today and for helping make this project possible.
Okay, are we ready, Dick? Ready? Ready? Okay, come on and cheer. Oh, he wants us to move close.
All right. Because this is the real corner. What Jorge's doing is setting the stakes for the boards that go on the outside of the forms for the concrete. And he just follows this line all around the entire thing and set stakes. And on that line we hang boards. We used recycled wood throughout the entire project as much as possible. In the perimeter foundation and the slab, we used 30% fly ash mix. The fly ash we used came from a coal plant in South Dakota, and fly ash is a waste product of burning coal to produce electricity. The fly ash replaced Portland cement, which would typically be used, and Portland cement requires an intensive mining and energy production to make. The pipes running to the rear go to the bathroom. The large one on the left goes to the toilet, which would be a permanent black water pipe, and the pipes on the right go to all the other fixtures, which would be a future gray water.
Okay. All right, now let's see, we're doing the underfloor plumbing.
Right. Under the slab plumbing!
One more step.
First we start out with the gravel bed flattened out and smoothed out perfectly flat. On top of that goes a 6 mil layer of plastic, and then 1 4-inch layer of high-density foam that is designed to be under concrete to take a heavy load. We foamed all of the edges with a foam gun around the edges of the foam as it's going in, and then put another layer of 3-inch foam on top of that to build up the 7-inch foam layer which would go underneath the concrete. So after we completed a full 7-inch foam bed on top of the gravel, we went around the edges of the foam and put in 2 inches against the concrete stem wall. That created basically a foam bathtub that would be filled up with concrete, so that in the end, the concrete would not be touching anything on all edges except foam, the bottom and all edges. Typically, the way we've always built is you pour a slab and the outside edges are not insulated and they leak an enormous amount of heat to the outside air or into the stem wall. Our slab will be fully wrapped with foam and not lose as much heat. And we're putting down a roofing tar compound here. It's a wet elastic compound, and the top plate of the first piece of framing will sit on top of this. And the reason we're using a wet patch is because when the plate goes on top of it, it will squish out and seal tight on the bottom. Typically, this isn't done, and air will leak underneath the plate and into the house. Oh, so this is real exciting. This is the first wall of the first passive house in California, going up in Point Reyes, and it was just an exciting time for me. That it's like we were really actually doing it, and I felt like we were the first man on the moon because we were doing the first passive house, and we were learning and making things up as we went along, and it was just an exciting time and exciting thing to do. What makes passive house unique and different from a typical house is meticulous air sealing of the entire shell. Super insulation that exceeds most California standards or national standards. So the passive house modeling system predicts before the structure is built the energy performance of the structure. And after it's built, the building has to meet that energy modeling. Passive house also has what makes it very different than any house that we build here is a HRV, a heat recovery ventilator. And what that does is it brings in fresh air, it exchanges it with the outgoing cooled air and stale air, and takes the heat that would ordinarily be blown out of the house and gives it back into the house. The build here is laying a bead of foam what will be the outside edges of the next sheet of plywood. If it was a window, the opening for the window would have foam around it as well. And in thus doing, the complete sheet of plywood is sealed around the edges, stopping any possible air movement from one sheet to the next and into the next cavity. Throughout the entire building, we use what's known as OVE, Optimum Value Engineering, also known as advanced framing or engineered framing. In this type of framing, you use 2-foot centers, you use a single top plate, and each rafter follows each stud, thus eliminating the need for a second top plate. Also around every window, as you can see in some of these openings, there's no trimmers holding up the header for the window. In this case, our headers are also insulated with a 2x6, a piece of foam, and another 2x6. The reason for this is to increase the R value of the header. Typically it would be solid wood, and you would lose an enormous amount of heat through solid wood. So the benefits of advanced framing is, number one, you use 15 to 25% less wood in the structure, which means less trees out of the forest. The labor is faster because there's less wood to assemble. And a great advantage is because there's less wood, you have more insulation. And these buildings calculate out to about an 8% increase in thermal resistance of the entire building because of the added insulation. We put a skin around the outside and sealed it. And we didn't put any windows in. We covered them over and everything was sealed. And then we did a first blower door test to see just how tight we got the shell. And this would be the outer shell of our ceiling. We came up with extremely low numbers in the teens, the high teens of CFM leakage. Okay, that's it. Low 12. That's good. Pie in the sky ring.
There are several factors about windows that we're interested in. One is the R value. The second one is their solar heat gain coefficient. And the third one is their air tightness. The frame is insulated and it's made out of fiberglass. So fiberglass is a better material than metal because it's less conductive. And the other thing is it doesn't move. It moves about the same as glass. So the seals, the air seals between the glass and the fiberglass frame stay pretty constant and move together, and so you don't have that breaking down.
The 2x4s above were staggered in between the 2x8 framing. This is another important factor to resist thermal bridging. If the 2x4s were set on top of the 2x8, the low R value of wood, hole would run through it continuous. When it's staggered, it runs through it and it stops and hits insulation. This is a future vent pipe that will vent the lavatory in the bathroom, and it's pre-stubbed out into what will be the air seal shell of the house. And this is a reverse roof jack. Typically these roof jacks go on the roof to keep rain out. In its reverse form here, what it's doing is it's keeping air from leaking in the shell to the outside of the house. So this is the boron-moron preparing a mixture of boron. Simply the boron is mixed with water, shaken up really well. Warm water works best, and then it's applied with a garden sprayer. And what I like to do is do 2 coats of it and go around once and then go around a second time while it's still wet. The entire structure as it was being built was doused and sprayed down with boron. Boron is a type of salt. It's an element that's mined. And what this will do will penetrate the wood a little bit, coat the wood so when how it's supposed to be that the termites come in and start to make a meal out of the wood. They'll have to eat the boron to get to the wood, and that will basically kill them. If you wrap the exterior of the building, in this case with 1 inch of extruded polystyrene, you have a continuous, unbroken thermal mass around the building. And this enormously changes the insulation value of the house. As the sheets went up, you can see Jorge here foaming the edges around the window, and as each sheet came together, they were foamed as well. All gaps everywhere were foamed, again stopping air from moving through the assembly. We used a cement board siding, which I really like to use a lot. It's not a wood product. It's made from cement and fiber, and it's extremely, holds paint really well. It's fire resistant, almost fireproof, and I think it's a pretty earth-friendly product again. After the outside shell was done, we began to pre-wire and pre-plumb the inside of the shell. It's a special airtight electrical box that we used throughout the project. So when the sheetrock goes against it, it is sealed tight. The wires go through this box and they're sealed through a mid-chamber that's filled up with foam. These boxes are extremely airtight and do not leak, as all outlets boxes do in all houses. Charles Bennett, the insulator, went and drilled an 1.5 inch hole through every end block of every rafter. The reason for this was he would come in later and from the outside and blow cellulose insulation into each cavity after it was sheetrocked. Just like the outside plywood was sealed on all of the joints and openings, the sheetrock was sealed as well on the interior. So here are all of the bales of cellulose insulation that will be chopped up in a machine and compressed and blown into the house. Here the insulator has a long 2-inch plastic tube which he inserts into each cavity to the roof and starts blowing in cellulose. As he packs in the cavity, he backs out the tube and keeps backing it out until the entire cavity is packed with cellulose. He goes inside the building and drills an 1.5-inch hole in each cavity, which is already sheetrocked, each stud cavity, and he will be blowing cellulose into each one of those cavities, this time using a flexible hose. The hose goes down to the bottom of the cavity and he blows and then backs out the hose until it's packed with insulation. The insulation gets packed to 3.5 to 4 pounds per square foot, which is known as dense pack cellulose insulation. And the reason you have to do dense pack is because it will not settle in the wall cavities and create any air gaps in the future. Cellulose has other advantages. It's made from recycled materials. It's shredded up newsprint. It's highly fire resistant. It's treated with boron. Insects won't go in it. And it also has a great advantage of being highly soundproof as an insulation in the wall. So after the cellulose is blown, all the holes are plugged and smoothed over, and we're now ready to begin the interior walls. So since we've established the inside shell is very airtight, all of the walls that are added on at this point do not have to be air sealed because they are inside the heated and cooled envelope. And they can have holes in them, they can leak, and they'll leak only into the inside shell. The shell was designed so that it had a minimal amount of wires and plumbing in it because each one was a puncture in the air seal. The architect designed it so that most of the punctures would happen in the interior walls.
Because the installation of the insulation is so critical about how well it's installed that you can deteriorate the R value very rapidly by having a poor installation. We wanted to use drywall, so we wanted to blow everything behind drywall because we'd get a better density, but you can't inspect it. So we see it, but we're going to get a person to come out with a very fancy infrared camera to go and make sure that it was all installed correctly. And so, sure enough, we got it installed beautifully. The infrared person said he'd never seen such great installation of insulation, and we got it to a higher density because we were able to put it behind drywall, so we got it even better insulation. So that was a pretty innovative sort of moment, but it took a lot of work. The heat recovery ventilator is made up of 2 duct systems. It's got the fresh air duct system and the exhaust duct system. So the fresh air duct will supply air to the living spaces. So it's always supplying a constant flow of oxygenated fresh air from the outside into those rooms. You have a constant flow of air out of those rooms. The exhaust air is full of heat that we're trying to keep inside. The fresh air coming in, it's bringing cold air in. By the time the two of them pass this heat exchanger, the incoming air is now hot and the outgoing air is now cold. The great thing about this heat recovery ventilator is it's got 2 fans that are blowing small amounts of air, 70 CFM, cubic feet per minute. So it's a very small flow of air. They calculate that a heat recovery ventilator saves almost 10 times as much energy as those fans consume, just because it keeps all of that heat that's being built up inside the building.
You might have like a 60,000 BTU furnace that would flame on whenever you need heat, and then it would turn off when you reach the right heat. This has a very, very small system for producing heat, and most of the heat is from the hot water from the roof, and if you really need it, it's a tiny little heat coil in the ductwork. So gone is the days when you need a furnace to supply heat to a house. So this is the coolest thing in the whole building. I love this. So the wall in the background, the white wall, is an already air-sealed sheetrock wall with insulation in it. The additional walls that you see are exposed 2x4s with plumbing and wiring in them. Typically, this plumbing and wiring would be in that sheetrock air-seal wall, and it would allow hundreds of punctures in the wall, and it would also take away an enormous amount of insulation. Now we're ready for a second sheetrocking, which goes on all the interior walls of the air-sealed shell. George, who performed the final blow door test, is what's known as the third-party verification for the airtightness of the building.
ACH calculates out to 0.36.
That's half of passive.
Jewish high-five. We designed the solar hot water system slightly oversized, so it would provide about 80% of the domestic hot water and space heating in the wintertime when there's less sun and more cold weather. So the hot water is generated on the roof in 4 panels. It's pumped down into 2 80-gallon storage tanks, which are in the utility room. The water is then ready for either domestic hot water or space heating. If the solar panels are not producing enough hot water and there's not enough hot water in the storage tanks, there's an additional 20-gallon electric backup hot water heater that bumps the water up to 120 degrees. If the house requires additional space heating, the hot water in the storage tank is pumped through basically a radiator that's in the incoming fresh air of the ERV that provides additional heat, space heating for the house. Here is Joel putting in a hot water recirculation pump. And the way these work, this is under the kitchen sink, is when you walk up to a fixture in the bathroom or the kitchen, you just push a button and it automatically starts the hot water loop in the pipes. In about 10 seconds, you turn on the fixture and it doesn't use any more than a half a cup of water down the drain before you have hot water coming out. It's a water-saving device. LEDs, the light of the future!
What Roger is setting up is wire connectors that wrap around each circuit in the electric box. We want to measure the electricity when it's used and how much is used. We're going to couple that with measurements of all of the temperatures of different things. So we're going to be able to therefore understand how much of this energy was generated from the lights being turned on, how much of it was generated by the stove and cooking, how much of it came from solar heating, how much of it was therefore left over for people, how much was heated by the solar thermal system, how much was heated by electric backup, et cetera, et cetera. So we'll have a whole understanding of, did this work as we modeled it, and where did we go wrong and where could we do it better. But also we want to use this data to go to the California Energy Commission and California Public Utilities Commission and say, here's a very low energy building. We did it all without expensive photovoltaics, and it's all about energy efficiency and energy conservation, and here's our data. And this is kind of what we think that the state should be shooting for in terms of getting to the zero energy buildings.
So just my final point is some people still believe that talking about environmental responsibility is an add-on to talking about affordable housing. Simple message, we're in the 21st century, there's no excuse, and there's high urgency to recognize that we have to think about the environment with every simple human act, regardless of its nature. So every house has to think about the environment and bring the environment in and relate to it in a responsible way, because the 21st century requires it. It's not an option. So let's dance.
And this is the exciting part of the world, right? This man in this organization called Clam doing this incredible work is just, for me, it's just, touches my heart. Thank you.
Thank you.